Swayam Prabha. Digital India. Educated India.
We are first going to discuss about a theorem which is known as theorem of total probability. On the right hand side you see a diagram which is known as Venn diagram. We have already seen Venn diagram earlier. In this Venn diagram, what we see, let B1, B2, B3, B4, B5, B6, B7 up to Bk here, they are all representing different events and they are part of the sample space, such that if we look at this diagram, Bi intersecting Bj is psi, this means null. There is no intersection between the events. Second thing, sum of these events is basically the sample space, that is S, and probability of each event is greater than 0. When the events as shown by B1, B2, B3, all these, when they are not intersecting each other, that means they are basically mutually exclusive. So in this particular case, the events are mutually exclusive. There is no overlapping between the sections which are shown here. So these are the part of this understanding the total probability. And now let us say A is another event with respect to the sample space which is consisting of B1, B2, B3, B4, B5 up to Bk. The k in this case may be 8, so we can write k as to be 8. If there are 8 different events and A is common to all of them. So A is intersecting with all these individual events B1, B2, B3 up to Bk. So therefore, we can write that A is having an intersection with B1, which is this part. Then it has intersection with B2, which is this part. It has intersection with B3. It has intersection with B4. Entire this whole thing is B4. Here we have B5. Then we have B6 starting from here to all the. So therefore, see, if I write what is A, the A is addition or summation of individual intersections. So A intersecting B1 union A intersection B2 union A intersection B3 union A intersection Bk. K could be whatever is the number. So that is what A. So we can easily understand what A means from the diagram itself. So Venn diagram is a very useful or powerful tool in this case to understand. And this is the boundaries also shown. So some sets of A intersection Bj may also remain empty. That is also possible. So all B's are basically mutually exclusive events. They are not intersecting each other. And A, in present case, I show you that A is actually intersecting all of them, but it is also possible that A may not be intersecting either B1 or B3 or B4. It is also okay. The theory will still remain valid. However, this does not invalidate the decomposition of A. We will write the same way, but then we can write that those intersections are basically null because nothing exists. There is no intersection between. We can draw another diagram where I can show you that A is not intersection of one of these, B1, B2, B3, B4, whatever it is, and then we'll write that that intersection is basically null. All the events A intersection B1, A intersection B2, A intersection BK are pairwise mutually exclusive. That means they cannot occur simultaneously. That is what means that they are mutually exclusive. They do not occur simultaneously. Like if I toss a coin, I'll only get either head or tail. I cannot get A and head and tail simultaneously. It is not possible. In a given experiment, I will only get either A or B. So I can say that while tossing a coin, the getting a head or getting a tail, they are mutually exclusive. If head occurs, then tail cannot occur, or if tail occurs, then head cannot occur. That is what is known as mutually exclusive events. Now, applying addition property of mutually exclusive events, which we have studied earlier, we can write what is PA. Whatever is written here, I only are putting P in front of it. And then we are writing P of A, that is probability of the event A is PA intersection B1, PA intersection B2, PA intersection B3, like that it will go on up to P intersection BK. So PA, probability of the event A, is the sum of individual probabilities of P intersecting with B1, B2, B3, B4 up to BQ. So each term P intersection Bj can be written as PA by Bj into PBj. This is coming from the theorem of conditional probability, which we have discussed earlier. So if we use that conditional probability, we can write this statement. That is, conditional probability is that I can simply write, if we try to recall, P A given B can be written as P A intersection B by PB. This is how we can write. So this is what is known as conditional probability. From there we can write P intersection B is how much? Therefore, PA intersection B can be written as PA given B into PB. That is what is written. Same thing I am writing here. So in that case, therefore, PA intersection B1 is PA given B1 into PB1. PA intersection B2 is PA given B2. This will be read as PA given B2. It's not P oblique A oblique B1 or A divided by B1. Don't read like that. That is, in this case, it basically means P probability of the event A given that B has happened. So in this case, if I read like this one, PA intersection B3, that basically means that B3 will come here into PB3. That is, given B3 has occurred, what is the probability that A has happened? Into probability of B3 event. So multiplication of these two probabilities will give you this probability PA intersection B3, that is probability that A and B3 has simultaneously they have happened or they have occurred. Intersection means that both of them are present together. Okay, so it will be, so each term in this case I can write like this, and that is basically like this, and therefore we can write okay, this is known as tree diagram. The earlier one was known as Venn diagram, and this is another way of representing the same phenomena in the form of tree diagram. In the tree diagram, see, this is the origin. From here you draw these lines, and these are the nodes, and nodes are representing the different events: B1, B2, B3, B4, B5, B6, B8, or BK. So these nodes are actually representing the different events. And then I draw a line, a horizontal line, and write that on the end of the line I am writing A. So A is something which is common to all of these events. That's why A is coming here. So this is the source. I draw a line. Here I am putting the nodes and put B1, B2, B3, B4, B4, all those events, and simply draw these lines, and this is what is called as tree diagram. So between the source and the B1 node, I write this is the probability PB1. This is just the kind of representations. And when it come here, we write this is PA by B1. That is PA given B1 has occurred. Next one is PA by B2, because this is node B2. So probability of A given B2 event has occurred. So like that we represent it, and both way representations can make the understanding simple and easier. So we can write PA, either you look at the Venn diagram or you look at the tree diagram. PA is the summation of all of them. So PA by B1 into PB1, PA by B2 into PB2, PA by BK into PBK, that is the last one. Here also, if you look at the Venn diagram, A is intersecting all the events B1, B2, B3, B4 up to BK. So PA is basically becoming like this sum. Then again there is a summation. So summation signs, look at these summation signs, these are all there, and I am writing like this. That is, if I write it, instead of writing it going up to K, if I simplify my writing, I can write it PA equal to sigma I equal to 1 to K PA by BI into PBI, by I varying from 1 to K. So this thing is known as the theorem that we are discussing. This is the final formula of this theorem of total probability. So total probability is the sum of individual probabilities. Okay, now this understanding will be clear once I discuss some numerical problems. So let us take one examples. There are 100 pieces of t-shirts, out of which 20 are defective and 80 therefore non-defective. If two shirts are chosen at random without replacement, what is the probability that second chosen item will be defective? So I am choosing two shirts. We need to find out the probability that the second chosen item is defective. And there is one more important statement here, that is without replacement. That is, the first item which is chosen, we do not put it back. It is separated from the lot. So once there are 100 pieces in the beginning, the first selection is done, and whatever is selected, whether it is the defective items or non-defective items, that is separated. So when I go for the second selection, there are only 99 t-shirts now left. So that's why this statement is important, without replacement. So whenever some numericals comes, you should be very careful about this, whether it is selected with replacement or without replacement. Because in the two cases, the probabilities will be different. Now, if I want to solve this, how to go about it? Let A I represent it. First chosen item is defective, and B is second chosen item is defective. Here the outcome depends upon what happened with the first chosen item. Was it defective or not? Okay. So in this case, I have two types of shirt, defective and non-defective. The outcome depends upon what happened with the first chosen item. Was it defective or not? It will be the summation of the two probabilities. One, probability that the second item chosen was defective, given that first item chosen was defective also, plus probability of the second item chosen was defective, given that first item chosen was not defective. Because when I am choosing the first item, then there are two possibilities. It could be defective or non-defective. If it is defective, then while I go for the second selection, one defective shirt is less now. So from 20, now we have 19 defective shirts and 80 non-defective shirts. But if it is first case, if the outcome is non-defective shirt, then now I have when I'm performing the second selection, then I have 20 defective shirts still left, but non-defective ones have reduced by 1 and it has become now 79. So therefore, all depends. So the probability will depend upon these two different possibilities which are there. We have to take care of it. So mathematically we can write that PB will be PBA into PA plus PBA bar into PA bar. PBA bar into PA bar. So A is first item chosen defective and A bar will be first item chosen not defective. That basically means. So PB is the summation of these two. PBA, given that A has happened. Given that the first chosen item is defective, what is the probability that the second chosen item will also be defective? So that is what is conditional probability multiplied by probability that A has happened. The next one is probability that first one has not happened. That A chosen item was not defective. So it is writing A bar. Given that A bar, what is the probability that second item will be defective? So PB slash A bar into PA bar. So if we look at this now, what is my PA? PA is 1 upon 5 because there are 20 shards are 20 defective shards are there and 80 non-defective shards are there. So sorry, this will be 100 total number of shards are there. So PA is going to be 1 upon 5 and therefore PA bar is going to be 1 minus 1 upon 5, which is 4 by 5, or I can write is 80 by 100, that is also 4 by 5. So I can write either this way directly 80 by 100, or I can write it as 1 minus 1 upon 5, that is 4 by 5. So PB therefore will be this probability and this probability. 19 by 99 into 1 upon 5 plus 20 by 99 into 1 minus 1 upon 5. And if I do this, I arrive at the figure 1 upon 5. This is probability that the second item chosen will be defective is going to be 1 by 5. This is one probability for one situation and this is another situation. Now we take another example. An item is produced in 3 factories A, B and C. It is known that the production of factory A is double of factory B and production of factory B is equal to factory C. Proportion of defective by the factories are 2%, 2% and 4%, A, B and C. If all the items produced by the factories are put into one bin and then one item is chosen at random, what will be the probability that it will be defective? So here the 3 factories are producing some item. It could be whatever item we can say. It could be some, if it is the garment factory, it is manufacturing shirt or trousers, or it could be, in the case of spinning mills, it could be cheese or cones, whatever it is, whatever items are produced. So if we want to find out the solution for this, let us introduce the following events. A, that the item is defective. B1, that the item came from factory 1. B2, that the item came from factory 2. And B3 is the item came from factory 3. And now the Venn diagram will look like this. There are only 3 factories B1, B2, B3 and A. This circle is representing the items which are defective. So it is intersecting with B1, B2 and B3, all of them. The corresponding tree diagram will look like this. So these are the factories B1, B2 and B3. These are the defective items. So PB1, PB2, PB3. It is PA by B1, PA by B2, PA by B3, like that we can write it. So defectives coming from factory B2 So PA by B2, if I write PA by B3, it basically means that the defective items coming from factory B3. So these are the ways you can draw the diagram in order to understand. Either we make both Venn diagram, or you also can make the tree diagram. Whatever you feel like, you can draw one of them or you can draw both of them. So I can write now PA in this case will be PA by B1 into PB1 plus PA given B2 PB2 plus PA given B3 PB3, because there are only three sources from which the items are coming. So if I want to know this, I have to find out these individual probabilities, and then we have to add them up. So that is from the figures, from whatever is stated in the example, we can write what is PB1.5, because this factory produces double the production of others. So therefore, whatever materials are coming here, the quantity of material from B1 is double of B2 or B2 B3 combined, whatever is there. So P of B1 is going to be 0.5, P of B2 is going to be 0.25, and P of B3 is going to be again 0.25. Out of the total, half is from factory B1. Rest half is coming from factory B2 and B3, and they have equal proportion because their productions are same. So we can write these are the PB1, PB2 and PB3 values. Now PA given B1, it is also stated that 2% are defective, 2% items coming from factory B1 is defective. So I write it PA given B1 is 0.02. Similarly, PA given B2 is also 0.02, and PA given B3 is 0.04. So these things I am writing because they are already stated in the example. So nothing to think straight away. After reading the numerical, you will be able to write these values. Now comes this statement, this particular formula, that is for total probability. In this case, it is limited up to 3, because there are 3 factories. So PA, if I want to know, I substitute the values simply. PA by B1 is what? 0.02. PB1, let us find out 0.5. So these two we multiplied, plus PA by B2 0.02, PB2 is 0.25, multiply these two, and third is PB3, PA by A given B3 is 0.04, multiplied by 0.25. That's, do this simply, add them, final result is 0.025. So solution up to the problems are not very difficult, very simple. So we will be able to understand whatever is stated in the examples, you have to read them carefully, and then the given values have to be written. So things will be easier if we make such kind of diagrams, and that understanding also will be better. So we have seen these two problems, they are not difficult at all. From there we go to the next theorem known as Bayes theorem. So Bayes' theorem is also based on the previous one, the theorem. So we need to now find out the probability. What is the probability that you want to find out? We'll get to know just now. Now, with respect to the previous example, if an item is chosen from the bin is found to be defective, what is the probability that it came from factory B1? That is suppose you are interested to know. That given that it is defective, now what is the chance that it is coming from factory B1 or B2 or B3? If this question comes to our mind, then how to get the answer? So we want to basically find out P B I given A. A indicates defective item. So we are stating that the item is defective. So given is A, it is defective. What is the probability that it is coming from factory BI? Or I could be 1, 2, 3, or whatever number of factories are there. We may have, this could be factory, this could be vendors also, that many companies will buy some item from different vendors. So as per conditional probability, PBI by A can be written as PA intersection BI by PA. This is what is stated, what we have learned already in the conditional probability. Condition is given A, BI is going to happen. Probability of BI given A has already occurred. And this is the formula which can be written. Understanding of the formula also is easy if we have the Venn diagram with us always. Venn diagram will make the thing clear in your mind. The tree diagram is shown here and the Venn diagram is also shown here. It's the same diagram which was there previous case, same diagram I have brought it here because we'll be using the same diagram. So how to find it out that given that it has defective, what is the probability that it is coming from factory BI, or I could be 1, 2, 3, 4 up to K. So how to go about it? Now PA intersection BI, I can write it as PA given BI into PBI. According to the theorem of total probability, PA is this. We have already learnt it in the previous case. It was there I to K, I have written it J equal to 1 to K. And therefore, PBI by A can be written as PA given BI into PBI, that is this one, divided by whatever is written for PA that we have found out earlier, this two. So we have numerator and this is my denominator. Denominator is the total probability of A, which is sum of the individual probabilities that we have already discussed earlier. That is the sum of P A given Bj into Pbj by j varying from 1 to k. So expression in the numerator is the probability of reaching A via ith branch of the tree. Because we are interested to know, given that A has happened, what is the probability that it is coming from the factory Bi? So this may be, let us say, A, and this is my factory Bi, or I can vary from 1 to k. So I'm interested to know this. So numerator is representing that is the probability of reaching A via the ith branch of the tree, and this is my ith branch. An expression in the denominator is the sum of the probabilities of reaching A via k branches of the tree. If this is my tree, these are the branches. So reaching k, when reaching here, so I am summing all of them through B1, through B2, through there are so many paths as if, or so many branches. I can reach A by this and this, all of them I have to include. That is what is the denominator is. So this is how the Bayes theorem is stated here. This is what is known as Bayes theorem. That is, knowing that something is defective or something is good, what is the probability that it is coming from a particular factory, or it could be particular vendor, or depending upon the situations, it could be factory or vendor or something else. So these are the theorem, and now we'll again take an example to fully understand this. So let us read this next example. A textile firm procures fabrics from three vendors: 60% from vendor B1, 30% from vendor B2, and 10% from vendor B3. If 90%, 5% fabric supplied by vendor B1 and 80% from B2 and 60% from vendor B3 are as per specifications, what is the probability that any fabric received by the firm will be as per specifications? And secondly, what is the probability that a fabric which is as per specifications came from vendor B3? So we want to solve this particular problem. So there are two questions which have been raised, and we have to find out the answer. First, we will have a Venn diagram. So in the sample space, I have three vendors. So I write B1, B2, B3. These are my three vendors. And A is the, we will be getting it as per specifications. So A has intersections with B1, with B2, and B3. So we have intersections here, we have intersection here, and we have intersections this way also, let us say. With all of them we have intersections because A is common to all three vendors. This is the corresponding tree diagram. I have only written it like this. A, in this case, A is not defective, but A is item received as per specification. They are the good ones now. So these three nodes, B1, B2, B3, so three branches you can say of the tree, and A's are there. So this one will be represented B, A given B1, then B, A given B2, it is B, A given B2, and these values are already given here. And here P, B1, that how much is coming from factory B1, how much is coming from factory B2, B3. So all these values are already stated, 60, 30, like these values are already given there. So I am writing, these are, all of them are already given. You need not to do any calculations or anything. %95% fabric supplied by vendor B1, they are as per specification. So we write PA given B1 is 0.95. So A is the proportion of fabric which is as per specification coming from B1. So we write PA given B1 is 0.95. Similarly, PA given B2 is 0.80. It is already stated. And PA given B3 is 0.65. These values are already there, here and here. So we are writing whatever is stated in the numerical, just simply write them properly. So when we go for part 1, we know we have been asked this value. What is PA? So PA will be PA by B1, PA given B1, PB1, PA given B2, PB2, PA given B3, PB3. And all the values already are stated. We simply substitute those values and do the simple multiplication and addition. That's all. And we arrive at the figure 0.875. That means the probability that any fabric received by the firm will be as per specification is going to be 0.875 in this particular case. Now we go to the next part of this problem. What is the probability that a fabric which is as per specifications came from vendor 3? So how will you write it? Given that it is as per specifications, it is coming from B3. So the way to write it is be this P B3 given A. Given that it is as per specifications, probability that it is coming from B3. So if I want to write this, this will be way to write the mathematical form. This is how we have to write it. And as per the formula, this is what we should write. That will be PA given B3 into PB3 and denominator PA given BJ. I can write A, BJ, PBJ, J. I is not from 1 to K. In this case, K is 3. So it will be 1, 2, 3. So if this is the expanded form of the same thing. And now we are supposed to substitute the values. Values are already stated in the previous slide. So simply substitute the values and you arrive at this figure, that is 0.074. So given that it is a fabric which is as per specification, probability that it is coming from factory B3 is 0.074. That is how we can solve such problems. And this kind of issues may come up also in the industries at times. And now one more problem that we are going to discuss. Example 4. Use information on the tree diagram to determine PA, PB given A, PB given A bar. So now only tree diagram is given. There is no text in the example, just an tree diagram. A figure is there and some values are quoted. These are the 3 values which are given here. We have to find out what is my PA or P B given A or PB given A bar. This is what we need to find out. So how to solve this particular problem? PA will be PA intersection B plus PA intersection B bar. That means PA given B, PB, PA given B bar, PB bar. See here, what I have, there is B and this is B bar. Then we have A bar, A bar. So from the figure, what we can read? How much my PB is, that is value stated 0.4. I can see from here this is 0.4, we write it 0.4. So what is PB bar? This value is not given here. But PB bar will be 1 minus PB. And therefore it will be 1 minus 0.4, it will be 0.6. So this value is going to be 0.6. Because PB plus PB bar has to make 1. Therefore, PB bar will be 1 minus PB, 0.6. And PA given B, that is also given, that is 0.3. This value has been given, already written here 0.3. So I write PB, PB bar and PA given B. But I have to find out all this to know what is PA. I need to know what is PA given B, PB. So PA given B only, that value is known. So this value is known to me. PB is known to me. But here PB bar is known to me, but PA given B bar, this is something we do not know. This part we still do not know. That is what we have to find out. So PA given B bar, it will be 1 minus P A bar B bar. See, point is this part is given. P A bar given B bar is 0.2. So this value will be 1 minus 0.2. It is going to be 0.8. Once we have this, now I can easily calculate my PA, use the same formula and substitute the values of PA given B, PB plus PA given B bar, PB bar. 0.3 into 0.4 plus 0.8 into 0.6. And that gives you a figure 0.12, 0.48, that is 0.60. So probability of A is going to be 0.6. Next comes PB given A. PB given A. So I write the conditional probability formula first. PB given A is PB intersection A by PA. So PA does not change. PB intersection A, what is the formula for that? If I write this formula, PB given A, PA. Same thing can be written PA given B by PB. These two are interchangeable. If we look back the conditional probability where the if you want to know the probability of the intersection area, then you will find that PB given A into PA is exactly same writing PA given B into PB. They are representing the same thing actually. So I can write this as this. Why I am writing this? Because this is what is known to me. So I write point PA given B, and I see this value is given here. 0.3, I write 0.3. PB is also given 0.4, 0.4. And PA, I've already found out 0.6. So I'm writing 0.6 here. And therefore it is 0.12 by 0.6. So this will give you a figure 0.2. So therefore PB given A is 0.2. PB given A and PA given B, see, they are different. PA given B is already stated 0.3. But what we have found out is PB given A, it is 0.2. So what is written here, already given, that is PA given B, what is 0.3. And we have to find out, given that it is A, what is the probability that it is B? It is coming from B. And now the last part. So this is a little kind of, you can say, writing like this is kind of algebraic treatment of the, if you have to practice a bit using a Venn diagram and the basics, the theorems and the which are there on conditional probability or intersections of two events, how to write them, and if you look back all those, and then you will be able to quickly write. The other thing now is that we have to find out what PB given A bar. So we need to know PB given A bar. This is what we need to know. PB given A bar. Not P A bar given B. P A bar given B is simple, but PB given A bar is not straightforward. So whatever we wrote earlier, all those values which are already given, we have written it here again, so that we need not to look back the previous slide. And P A given B bar is how much? Then is this data will be how much? PA given B bar is 1 minus PA bar B bar, that is this, and this will be actually 0.8. So PB given A bar, I can write is PB intersection A bar by PA bar. PA bar we write P1 minus PA, and PB intersection A bar is, this is the conditional probability. We write directly the formula of conditional probability. From conditional probability we can write this. PB intersection A bar is PB given A bar into PA bar. Now this one again is replaced. This one is replaced by this. P A bar given B into PB, because they can be interchanged. Denominator remains same. 1 minus PA. Now I can write P A bar given B is 1 minus PA given B. Therefore, it will be 1 minus 0.3. That is, this value is actually 0.7, which is P A bar given B. But I have to find out P B given A bar. So they are not reciprocate. So we'll write like this, and what is happening here? 1 minus 0.3 is 0.7 into 0.4 divided by 1 minus 0.6 is also 0.4. So 0.4 and 0.4, these two will cancel, and we will be left out with 0.7. So this is also coming to be 0.7. PB given A bar, so PB given A bar is coming to be 0.7. With this, we close this particular session on the second, you can say, session on the basics of probability, and you have to, as I said earlier also, the more you practice, the more you learn. So you take some standard textbooks of statistics and solve many more problems. With this, we close today's session. Thank you.